take some notes about the concept of power. And I'm going to start out with an example. We got a sports car with mass 1,000 kilograms, can accelerate from 0 to 30 in 6 seconds. Mr. Lynch's car at the same mass can do the same acceleration, but it's going to take 120 seconds. So which car performs more work in accelerating from 0 to 30? Remember, work is going to be the change in energy. In this case, it's change in kinetic energy. So we can just find that the kinetic energy at the beginning is 0, and then it changes. Let's say we're going for the sports car to what value? So KE is 1/2 mv squared, 1/2 times mass 1,000 times velocity of 30 squared, and that's going to give us a value for the work done, 150,000 joules. Now, you may notice that the time doesn't enter into it. Okay, work has no time element to it. It's just a change in kinetic energy. So the fact that the sports car did it in 6 seconds and my car takes 120 seconds doesn't really matter. Okay, so they have the same amount of work. So if we ask a different question, we say which car is more powerful, we're going to say it's the sports car, obviously. It can do the same amount of work in less time. All right? So, our definition of power then is going to be power is the rate at which work is done. And mathematically, we're going to say power is work divided by time. Now, there is a lot of ways to get work, right? I could say that's change in energy over time. The other way to get work is Fx theta. That divided by time to get power. And there's one other one. If I look at this, I have an x divided by t, a distance divided by time, in the middle of this equation. X divided by t, distance divided by time, is average velocity. So it can also be that. So for the example, it says what's the power in each car in the problem above. So we'll do the sports car first. Okay, the power. Okay, we're going to use work over time in this case because we already have work. The work was 450,000 joules. So 450,000 joules divided by the time of the sports car was 6 seconds. So that's going to give us a value of 75,000 joules per second, or 75,000 watts. Okay, watts is the unit of power, and a watt is equivalent to a joule second. So when you say you have a 100-watt light bulb, you're actually telling the power that light bulb is using. Now, if we do Mr. Lynch's car quickly, okay, it's going to be P of T. It's the same 450,000 joules divided by the time. This time is 120 seconds, and we get 3750 watts. Okay, so about the power of a toaster. All right. Now, we've got a couple of example problems here. How much energy does a 100-watt light bulb use in 12 hours of continuous use? And then it says express it into joules and kilowatt hours. The reason I'm doing that, sometimes you see kilowatt hours, it's how the power company charges you for energy. So I want to do an example of that as well. So if I want to do it in watts, have to remember watt is a joule per second. So I need to make sure that my time is in seconds. All right, so the first thing I'm going to do is my time is 12 hours, 12.0 hours. I'm going to multiply that by 60 minutes per hour, and by 60 seconds per minute. Those all cancel, and I'm left with seconds. So my time is 43,200 seconds. And then I can just use the equation P equals W over T. The power was given as about 100 watts. It says watts, so that's going to be the power. So 100 equals work over 43,200. And then I'm going to end up with the energy I use is going to be 432. 4 zeros after it. 4,320,000 joules. Now, if I want to do it in kilowatt hours, it actually is a little bit easier. In this case, I can have my time in hours, but I have to have the power in kilowatts. Remember, changing from grams to kilograms, I have to move 3 places. So it's the same thing in going from watts to kilowatts. So 100 watts, let's move 3 places, going to be 0.1 kilowatt. Okay, and that's my power. Then using that same equation again, P equals W over T. I get 1 kilowatt, 0.1 kilowatts, equals the work divided by, and now I can leave my time in hours, so it's going to be 12 hours. And when I cross multiply, 12 times 0.1, it's going to be 1.2, so I get 1.2, and my units are, I just took a kilowatt number and multiplied it by hours, so it's kilowatt hours. So that's how to deal with kilowatt hours. On the next page, we have one last example. Okay, a person pushes the couch with a force of 1,000 newtons at constant speed of 2 meters per second. At a distance of 5 meters is 2.5 seconds. What is the power? In this case, I have a force of 1,000. Okay, I have a velocity of 2 meters per second. I have a distance of 5 meters. 5 seconds. There's going to be more than one way to do this problem, but my equation the easiest way, since I have force average velocity, is just the power is force times average velocity. There's no cosine theta in this because if you're pushing the couch, it's going to go in the same direction you're pushing it, so I don't have to worry about any weird angles in there. So now my power is going to go to force, which is 1,000, times my velocity, which is 2, and that's going to give me a power of 2,000 watts. So there's a lot of extra information that probably didn't need. So that's power. I think you're going to find it's pretty easy.